applicable to, we're going to apply it to our circuits. So here we have a transformer. We have a primary side, we have a secondary side, and we're supplying these loads here with the transformer. I'm not showing breakers or the power distribution in the circuit, but just because we want to understand what's happening with the current here. So let's presume that we have 120 volts. Let's do this section. Let's presume that we have 120 volts.
You alright?
From here.
Just them tired, bro.
120 volts from here. So this looks like I've drawn a single phase circuit, which means that in a single phase circuit, half of this is going to be 120 volts, but from here to here is going to be 240 volts. So you have 240 volts from this location to this location, and 120 volts from here to here. Right? So when we're testing this, we're testing from essentially our neutral to our neutral to our hot, and then from our hot to our hot. You guys have seen these circuits like this all your homes, probably just like this. You probably have some circuits here like this. Yours are mostly three-phase, but we're just going to look at single phase now to simplify it. What I've done here is I've drawn the ground symbol. The center tap of your transformer is always going to be bonded to earth. It's been earth. So you have on your transformer somewhere, it's bonded, and then you're going to have a ground rod, or you're going to have a grounded electrode conductor coming out. That's going to be connected to your building steel, or your U for ground, or ground plate, ground ring, or maybe all of the above. It's going to be,
not at all.
well, it should be, and if it's not, that's something that you want to be able to find out if it is or not, and then fix it. Because they all have to be, your system has to be grounded.
I found the copper wire in the house. It's coming out where the hose spigot is.
Uh-huh.
And it's not connected. It's just sticking out. And I don't know if that copper wire. I gotta trade. I gotta see if it connects to the water here or not.
At one point in time, in homes, they used to take in your water pipe, they used to connect like one thing to another. So if you had a water heater here, and you had a pipe coming in, cold water here, and hot water out, they would bond from one side to the other. I don't think that's required anymore. Alright, so you guys understand what I've drawn up here, the application of it. We have two loads here on the other end. We have a 60 watt load, let's say it's a light bulb. We have a 60 watt light bulb, and we have a 100 watt light bulb. So, from what you guys know of Ohm's law, how many amps is this 60 watt light bulb using? We got watts, we got volts, we have amps, we have resistance. Watts, volts, amps, and resistance.
Watts divided by
0.5.
Okay, so we have watts divided by our voltage, which is what?
120.
120 volts. Divided by 60 watts. So we're actually, that's worded that incorrectly. We're using the right formula, we just have the numbers reversed. So our watts is going to be divided by 120. So a watt is divided by our voltage. So, John, did you say 0.5? So if we take 60 watts, we divide it by 120 volts, we're going to have 0.5 amps. You guys see how we've come to the wattage of this light bulb? What's our resistance?
So it would be volts divided by amps.
Volts divided by amps?
Yeah.
Is 120 divided by 0.5?
60?
6.0.
Should be 240. 120 divided by 0.5 should be 240 ohms of resistance. Alright, so one thing I haven't explained yet, and I'll do that now, is the watts changes. The volts change, the ampacity changes, but the resistance never changes. So we have a 60 watt light bulb, it has 60 watts on it. Does that mean it's using 60 watts? About 60 watts. When we say we have a 120 volt circuit, that's a nominal voltage, which means that we could have 110 volts, we could have 115, 125, 117. It just means it's about 120 volts. Our ampacity is based off of our voltage and our resistance. Our resistance is fixed. Resistance is always going to be fixed. So let's solve for the 100 watt light bulb. Our wattage was 100 watts, right? 100 watt light bulb. What's our voltage?
120.
Back again to 120. Our ampacity is
83.
83.83 amps. So less than an amp. Still. What our resistance is?
240.
240. You guys think you can all solve? I know some of you were spouting out the numbers, but you guys all know how to be able to solve for these?
I just trying to place the division or multiplication.
Not quite. So we took our wattage, divided it by our voltage, which ended up being our ampacity. We took our voltage, divided by our ampacity, and equaled our resistance. It's the formula on the other page. When you flip the page over. What was that you were saying? So, if I check my ampacity on this conductor again, how many amps am I going to have? 0.5. If I check my ampacity on this conductor, how many amps am I going to have?
0.8.
If I check my ampacity on this conductor, how many amps am I going to have?
0. 83.83 plus 5.
Plus 0.5.
Have you?
0.88.
You guys probably haven't heard this.
1.3.
So our neutral on a multi-wire branch circuit always carries the unbalanced, carries the unbalanced load. So if we have a three-phase circuit, which is what you guys have here typically, you're probably leaving from your panel, you have three hot conductors. You have probably, say, a brown, orange, and a yellow. Is that the colors that you guys have seen out there in the field? Brown, orange, and yellow?
White, black, red.
Okay, so black, red, blue, because you're gonna have three-phase circuits. So you're either gonna have black, red, blue, or you're gonna have brown, orange, and yellow. Brown, orange, and yellow is a higher voltage, 277, 480, and black, red, blue, 120, 208, 240. So if we have our three-phase wires, or three different phases going out, and they're all taking 10 amps on each one of those conductors, our neutral coming back would be 0, even though they're feeding separate loads. Why? Because it's only carrying the unbalanced load. So if I take 5 amps on this wire, 8.3 amps on this wire, I'm really going to see 2.5 amps, whatever the difference is. I'm going to take 0.83, divide or subtract 0.5 from that, and that's what's going to be on my tester. So you need to be careful when you guys are troubleshooting things out in the field. If you're seeing, like we talked about today, hey, I got 5 amps on this wire, or 0.5 amps on this wire, I'm going to have 0.5 amps going back on this white wire. Don't assume that that's true, because it actually is going to be only the unbalanced load is going to be coming back on the neutral. Some of that's essentially coming back on this one. So we have the unbalanced load coming back on our neutral, but we're doing electrical work, we're troubleshooting circuits. Mostly of what we're doing, we're not designing things. So let's create a problem. We've lost our neutral. So now it's not carrying the unbalanced load. If I put my amp probe here, how many amps am I going to see?
0.5.
Ah, you made an assumption.
It's the,
The
Oh,
fact
but we
is,
might be getting,
everything just
83.
changed.
83,
Everything changed.
0.5, plus 0.5.
My hope is that the breaker trips, but sometimes the breaker doesn't trip. And when you lose a neutral, sometimes the breaker doesn't trip, but your field things change. Now, we've just changed our values here by opening up our neutral. These were our previous values when the circuit was working properly. Once that neutral came apart, and sometimes it's accidental, not just a field failure. If I'm opening up this light switch, and there's a white wire, a red wire, a blue wire, and a black wire, all coming into the switch, and then I have the regular lighting, but I have a three-phase, a multi-wire bright circuit coming in from the panel. Does everyone know what I mean by multi-wire bright circuit? Okay. I don't want to confuse you, so let me explain this. So I have at my circuit breaker, I have 3 circuit breakers in my panel that are interconnected with a breaker tie. Have you all opened up a circuit panel before? Okay, good. So you open up your circuit panel, you're going to see some of those breakers are tied together with a little bar. So this symbol, when you see in this schematic, whether it's in your plans or whether it's in an electrical drawing, this little dotted line here means that these breakers are tied together.
With a bar?
Yeah, with a bar, with a
you're talking
bar.
mechanically, like,
Mechanically tied together.
okay.
So if this breaker trips, it's going to trip the other 2 as well.
All 3.
And if you go in there and you want to turn off this breaker, you're physically going to turn off these other 2 as well. And that's important because you have 1, 2, 3 wires going back in the field, and I'll use the blue for our neutral. We have a neutral going back. That neutral for that 3-pole breaker, let's say this is feeding a receptacle. And it goes to our neutral, and this one is feeding a receptacle. And then it goes to our neutral. And this one is feeding a receptacle, and it goes to our neutral. If we have 3 different receptacles feeding specialty equipment, if I go to that first receptacle box and I open up that neutral because I'm resplicing and repigtailing, I just opened up that neutral for not just this receptacle, but I've opened it up for this one and this one. And I've just created this problem with my receptacles, whatever's plugged in there. So we don't want to do that. We physically tie these together because when we're working on any of these, we have to turn it off. Let's go back to lighting. So we've just opened this circuit. Our values have changed because we're no longer using this as a path. Our circuit numbers have changed. But what doesn't change?
The resistance?
The resistance doesn't change. The resistance of these filaments has not changed. So our wattage changed, our voltage changed, and our amp capacity changed. So if I put my amp probe back on here, I don't know what I'm going to read. Hopefully it's going to be accurate to the circuit, but we'll discover what that is now. One more thing. So these incandescent light bulbs, one's 60 watts, one's 100 watts. Will they still operate? Is my first question. And second, which one will be brighter?
Which one will be brighter?
Which one was brighter previously? 100. So now which one's brighter?
Should be equal.
60.
Oh,
Will it even work?
volts up, current down, so it would be,
That's a good question. Will it even work without the neutral?
All right,
Is the 100 going to take more amperage than the 60?
Both of them, I don't
let's
think
find
current.
out.
Yeah, you can dig in the loop, so.
Let's find out. So, what do we know now? We've opened up our neutral. We have 240 volts from this wire to this wire. What is our circuit here?
it's a series
We had
circuit.
120 here. Now what do we have?
240.
We have 240 volts from this to this. Just like when we talked about series circuits, we've lost 120 volts. We no longer have 120 volts. We only have 240 volts. If I take my tester out and I test it anywhere along this line, it's going to be 240 volts. If I test it here, it's it's gonna be different, remember? Because we're gonna lose voltage drop here, or voltage drop here. But if I test from here to here, it's 240 volts. So our voltage, I can't write down 240 volts here just yet. You know what, this isn't right. They can't both, they're both not 240 volts.
Resistance is
Ohms.
1600.
Which one were
This
these?
one's 120.
Is this 60?
Resistance
Oh, it's all
is 60.
wattage. This is wrong.
The
60
voltage
watts.
should be constant.
240, 240. 100 watts, 120. 120 divided by 80.83 is what? Because it's wrong.
120 divided by 0.83.
Oh,
So it's 144.57.
144.57. All right, so this one has a lower resistance than this one. This was a 100 watt light bulb, this was a 60 watt light bulb. And now we have 240 volts. We can't put that 240 volts here because this is our voltage drop. This is our voltage drop. So we can't just put that over here. We need to solve for our total resistance here, which is what? How do we solve for total resistance in series circuits?
Add.
We add. We're adding this value to this value, or each resistor. We're just gonna add them together, which is 384. Let's see, so we have watts, volts, amps, and ohms for R. It's 384. Let's just call it 80.
0.57.
Let's just call it 84. Alright, so we have, this is our total resistance of our circuit. What's our total voltage?
Oh,
240.
240. We don't need to know our wattage just yet, but what's our ampacity? 240 divided by our resistance, right?
1.3.
240 divided by 30.65.
0.65?
Yeah, 625.
Oh, 625. Alright, so if I check the wire here, I'm gonna have 625 amps, 65 amps, 65 amps, 65 amps. How many amps did I check here? How many amps did I check here? Is he right?
Zero before?
It's gonna be 0, because there's no path for the current to flow. Electricity, it starts here, it ends here. Or vice versa, it starts here and it ends here. It's not, this is not a path anymore. But what happens if I check for voltage between here and here? Am I gonna have a difference in potential?
120 still.
No.
Get it, 240.
The answer is whatever this voltage drop here, this resistance is what this is gonna be. So I don't know. We'll find that shortly. So we have 6.25. Our amps for the whole circuit. On a series circuit, our amps here is going to be the same thing as our amps here. So this is 625 and 625. Is that helpful? Now we can solve for our voltage drop in each of those light bulbs, right? So what's our voltage drop here? I'm sorry.
Resistance.
Resistance times ampacity. So 240 times 0.625
Equal your vote.
equals our volts. And what is that value? Huh?
I don't know, is it divide or times or?
150.
Formula on it.
It's the Ohms law on the page.
From the ugly.
So you said 150? 150
0.6.
volts?
It's all Greek.
What about here?
That would be,
Sounds like a lot of people are getting it though.
No, just
Just refer to your sheet
90.
on these two formulas here. You said 19?
90.
90. Alright, so 150 plus 90 is equal to 240. So we've just shown that that's the correct value. Did you round that? Because this might have been rounded. Or maybe not. So we can solve for our wattage now. How many watts here? 90 times 0.625. Volts times our amps.
90.65.
90 times 0.625.
So 90.
56.
90.65.
That's 2.625
I know that's
56.
wrong.
equals 56.
56? Oh, apparently I don't know how to write 6. So 90 times 0.625 would be less than 90, it would be like almost half. So we're almost half there. So volts times amps here. So how many watts do we have on this one? 150 times 0.625?
93.
90.
Rounded to the nearest hundred, it'd be 94, right?
93, that's 94.
94.
I told you 66 lighter.
0.62.
Right.
93.75, I think that would be 94.
So Ruben says the 60 would be brighter. So it would, would it work? Would these lights work?
Yes.
Generally, these do work when you do this. I've done this before as a test.
So.
A 60 watt light bulb.
Would be, that 60 would be brighter than 100.
The 60 would end up being brighter than 100. 100 would either be very dim or you wouldn't be able to see it at all. The 60 would be bright, but maybe for a little while until it burned out. And then once it burned out, we have an open circuit and we wouldn't have anything on at all. Does that surprise you guys? Now, in this particular circuit, they're filaments.
We'll change it to motors, and what happens?
This would be bright, and this would be dim. But if this was electronics, this would just be, you'd be letting out the smoke. You're just gonna fry something. What happened is, for a long time, people were changing out old light fixtures, the T12s with the magnetic ballast, to the new light fixtures with the electronic ballast. And they would have multi-wire branch circuits. Then in being a light fixture, they would open up that neutral, and they would do exactly the same thing. The magnetic ballasts, which were the higher wattages, would not get burned up, and the electronic ballasts would fry. So this is something that you need to be really careful when you guys are working on electrical systems here. If you're working on something hot because it needs to be hot, you have your PPE on and your work tools for hot work. You need to make sure that you don't open up the neutral that's on a multi-wire branch circuit because you're likely going to fry something. We don't even use incandescent light bulbs anymore. Everything you use is going to get cooked. Everything has electronics now.
And how you tell the difference between the balusters?
Like the light fixtures?
The light fixtures and balusters? Because we got a lot of replacement ones over there at the building.
You probably don't have any I hope you don't have any magnetic anymore. In that building over there, you might have some magnetic ballast because I think you have older fixtures in there. If it's a T12, which is, the 12 stands for 12ths of an inch, so it's basically an inch tube. I don't know what these are. These could be LED for all I know. But if the T12 is a bigger lamp, and the T8s are smaller. So if it's a T12, there's a 50% chance you have magnetic ballast versus electronic. And you wouldn't know without opening it up, and you'll be able to see that's whether it's electronic or magnetic. It'll say on there it's electronic ballast. Okay, any questions about this? You guys got this? All right.